Hello everyone again, Jim Malis. I am looking to now talk about Chapter 4 a little bit. Let's see what we can do. There were some interesting problems associated with this, and it's 2- and 3-dimensional motion. Before we go to the actual problems, let's give you a little bit of a discussion pertaining to some of what is being said there. For Chapter 4, we've got 16, 19, 20, 30. Now I already wrote these down earlier in another video, but I'm writing them down again because we're going to directly do our best to try to do them right now. So here it is, guys. Chapter 4, we're going to try to do problems 16, 19, 20, 30, 38, 39, 40, 49, 60, 68, 70. Okay, 2- and 3-dimensional motion. What's going on here? Guys, it plays the same way as the vectors played earlier. I mean, just like, remember how we were adding vectors and all this other stuff that we could say here? We could say that, remember, for example, let's just keep it at this level. You said we had a vector like this. A lot of ways you could write this, I guess, but let me try to stay consistent with previous ways of writing stuff. And so let's see what we have here. So I'll make sure everything's turned on right, guys. Okay. So, yeah, that's true. This can work with a whole bunch of things, guys. You can call this, you can write this when you're talking about displacement, a displacement vector, like how far apart something is, how far away something is gone, let's say. We got this. Whole lot of stuff. I mean, you could write it like this, d sub x, d sub y, or you could actually, it's a number of ways you could write it. Yeah, this is fine. The way I wrote it right here is fine. You could also write it a different way, maybe a little better. X component I hat, Y component J hat, probably a little better. Z component K hat. So, could look something like this, you know. A lot of times they'll call this different play the D vector, displacement vector. Sometimes they'll call it R for radius away from a particular point. The R vector equals X I hat plus Y J hat plus Z K hat. X, Y, and Z are scalars. I hat, J hat, and K hat are unit vectors. Unit vectors long. That's location. Velocity vector, again, for those, this is a 209 class for which I'm doing a calc-based class. Anybody looking at it outside of that, you don't, if you're not, it's not a calc-based class, you don't have to do this, but for us, we do have to do this. This right here, the V vector, is dr vector dt. The r vector dt is each one of these. You're doing the time derivative in each part. Doing the time derivative in each part. Acceleration vector is the rate of change, because really the way this stuff plays out, guys, I mean, I try to, as we said, this is what we're going to be doing. You could talk about location, as we said earlier. R vector is x I hat plus y j hat. let's say we were not using calculus. Well, right here doesn't matter. That's fine. V vector would be delta r hat over delta t. That is the non-calculus, that's the non-calculus analogy to the calculus analogy right here. All right, so let me erase this right there, guys. I wrote down what the problems are. You got them. You can always go back on the film and look at it again a little bit, but this is where we're trying to go. So if you're looking at this, guys, just for the sake of getting a good idea of what we're doing here, delta R, delta T, that over there is the non-calculus analogy to what's going on in the calculus realm. And that would be delta X over delta T I hat, delta Y over delta T J hat, delta Z over delta T K hat. Acceleration is the change in velocity over change in time. What does that mean? That means, how would this change? You know what I mean? How would that change? You know, like, in other words, how would the velocity change? Change in velocity over change in time. And that, you know, the way that plays out is a little different. It's a little harder analogy to make. But this is exactly what's going on here. In the calculus realm, that is delta V delta T, or that's dV dt, and that is d of dr vector dt. At the end of the day, it's the second derivative, guys. And that comes out to second derivatives all over the place. So on and so forth. So what we got here is and that's where we're at. So I guess, you know, the analogy here, it's again, it's a tough analogy to go for. You're basically going delta, the delta of the delta. You know how that's, you know, now how you gonna play that in the realm, you know, in the limiting process. In the limit, if you take this to the limit, if you're doing deltas like this, if you're taking care of this kind of stuff, you know, there's a lot here. I mean, there's more I can write here. Not sure how helpful that would be to you at this point, but know that this is what's going on. You got this right here. You got that. You got the R vector. You've got the V vector. You know. Which is, you know, the delta R vector, delta T, and you got the A vector, which is the delta V, delta T. So yeah, that's all I've been doing right here, guys. That's the same exact thing I did right here. This is how the analogy works. Here's the R, here's the V, here's R vector, here's V vector, here's A vector, and wow, if you really want to get somewhat, you know, somewhat interesting about the whole matter, you can kind of write it like this. The way this would play out, this right here is the analogy. Delta V divided by delta T. delta V divided by delta T is analogous, the calculus analog to that is dV dt. And which also is this, analogous to what I wrote over there, and then it comes down to here. That's a little more. But anyway, that's a lot of what goes on related to some of this stuff. Let me try to think here, guys. I'm trying to figure out exactly what I want to say. There's a number of things that can be said. Now, we said what we said here. This stuff becomes much more manageable when we start doing the actual problems. I've always been a real huge fan of doing problems for people because within the context of doing the problem, we can discuss a lot of things. So we're actually doing a lecture at the same time we're doing the problem. There's no better way to visualize a problem than to visualize the problem, and that is look at the problem. Mathematics and physics is about solving problems. We do not know the mathematics and the physics unless we can solve the problems. I'm going to do my best to teach you how to solve the problems and tell you some of the background behind it. Well, here's some of the mathematics, some of the background behind some of the stuff we're doing here. Let's see what else we can kind of say here, and we'll take it from there. Okay, well, there's a lot of other things that go on, I guess you could say. There are I'm trying to figure out a good way to proceed with some of these arguments that can be done here. Let me kind of put some of chapters 4 and 5. This is chapter 4 that I'm working on right now, and then we're going to go into chapter 5 at some other point. But let me kind of hit a bunch of things at once. There is the idea of things that Newton said. I'm going to get into it in more detail when I actually get into chapter 5, Newton's 3 laws of motion. Maybe not. Maybe I'm not going to worry about it too much right now. I'll do that more for chapter 5, you guys. Let's say a couple things. Let's say you got a bird's eye view of a circle. Bird's eye view, you're above and something is whirling around the circle. There is an object whirling around the circle, and we'll get into more detail on this in the future. As I said, near future actually. But for right now, this object is whirling around. It's moving this way. Everywhere it moves, its velocity is tangent to the circle. If the string got cut, or if it was an old-fashioned slingshot, David and Goliath story, so to speak, bam, let go of the string in a sense. Whatever's there, if your aim is good, gets fired out at an angle. Angle's not the best word. It gets fired tangent to the circle. Everything taking off from that circle when the line gets cut, either purposely or non-purposely, when the line gets cut, everything takes off at a tangent. Well, we'll get more into this in the future. My gut feeling is this. If the object is very massive, I better be pretty strong to be able to whirl it in a circle and keep it in a circle. And I better have it moving really fast. The faster I make it move, the harder I got to pull on it. And the more massive the object is, the harder I got to pull on it. So there's two things here. If it's very massive, I probably have to pull on it really hard to keep it in a circle. And if it's going really fast, if I want to make it go real fast, it's also got to be held really strong. I've got to constantly make this thing stay in a circle. This thing does not want to stay in a circle. This thing wants to fly out of the circle. This thing wants to fly out of the circle constantly. It constantly wants to go tangent to the circle and fly off. What do I have to do? I have to not let it do it. I have to constantly pull it inward. For me to constantly pull it inward, I've got to exert a force and bring it in. Well, force equals mass times acceleration. We'll get more into this. That's Newton's second law. Force equals mass times acceleration, so I got to have an acceleration. I think it's hard to say. What if I were to say to you, you know what? What are we talking about here? If this thing's got a radius r and v and v is the velocity, is the magnitude of velocity, and let's say it's whirling around at 20 meters per second. Always 20 meters per second. Well, how's that an acceleration if you're not speeding the thing up and if you're not slowing it down? If you're not slowing it down and if you're not speeding it up, there's no acceleration, somebody would say. I would disagree. You are constantly forcing this thing to stay in a circle when it wants to go in a straight line. You are constantly moving it out of the path that it wants to take. Changing its direction constantly is also an acceleration. In fact, the magnitude of that acceleration is v squared over r. This is meters per second. When you square it, it's meters squared per second squared. Divided by meters, that's meters per second squared. The units are even right. There's a lot that goes on to prove this. I'd rather be in person talking to you about the actual proof of why that's true. For right now, let's assume it's true and let's believe it's true. Let's at least, in sort of a hand-waving fashion, or in a sort of, how do you say, kind of a gut feeling fashion, we know that if it's going really fast, you are going to have a hard time making it stay in a circle. You're going to have a hard time veering its velocity away from where it wants to go, away from the straight line that it wants to go in. You're veering its velocity constantly in a circle. You're constantly changing its direction. You're constantly changing its velocity. That's hard to do the faster the thing is moving. So you better have a good acceleration if it's going really fast. If you make the turn really tight, we know that on your car and on your body, when you make a hard turn with your car, you feel it more so than when you make a turn that has a large radius of curvature. If I take a turn really wide, if I'm allowed to do so, nobody's going to get hurt. If I just take a wide turn and just kind of take it easy, there's not a lot of stress on my tires. I don't hear them squealing too much or anything. I can get around. If I take a sharp turn, I might even spin out. My tires might not have the friction to keep me in that tight circle. So the tighter the circle, the harder it is to make the turn. And the faster it's going, the harder it is to make the turn. Well, a tight circle means small radius. Great velocity means big number for v. So inversely proportional to the radius, the acceleration, they call it centripetal acceleration. The centripetal acceleration is an inward directed acceleration goes inward. Let me just see if it's legible. I hope it's legible, guys. Yeah, it looks pretty good. All right. It's an inward seeking acceleration. The centripetal acceleration is directly proportional to the square. The centripetal acceleration is directly proportional to the square of the magnitude of velocity divided by the radius of curvature. Put it another way. The centripetal acceleration is directly proportional to the square of the velocity and inversely proportional to the radius. Inversely proportional to the radius, that means small radius, big centripetal acceleration. Small radius, big centripetal acceleration. Big radius, small centripetal acceleration, relatively speaking. Directly proportional means big V squared, big AC. Small V squared, small AC. Simple as that. Okay? With that in mind, there's a lot that goes on here. And you get tempted to do various things here, I guess. They've got this idea, and we're gonna, like I said, we're gonna get more into this in the future. It's hard to know when to start introducing things that are gonna be in different chapters. It's a bit challenging sometimes. But let me say a couple things. We'll say theta is the angle. Now angles, guys. Let's talk about angles a little bit. Angles can be in revolutions, they can be degrees, or they can be radians. Angles can be in revolutions, they can be in degrees, and they can be in radians. Radians are really popular. Radians work real good. Why is that? Well, didn't I tell you that the radian was the arc length S, we said that last time, arc length S divided by R. You can call the arc length, you can call it D if you want as well. That's not a real big deal. S or D or whatever, D for distance. The distance traveled along the arc. If that's the case, you guys, so you call it this. You can call it distance traveled along the arc divided by R. If you multiply by R on each side, theta times R. Or like I said, if you just want to keep it like this, I don't know, you can argue this a whole bunch of ways. It's not a big deal. That works. That works. We'll use that in the future a little bit. Let me come back to this one. Let me just come back to this one. The symbolism might be a little easier with what I'm about to do. Arc length divided by R is theta in radians. It only works for radians. S is theta times R. If it's going in a circular path, let's talk about magnitude now. Let's not worry about a vector, but it is a vector. Don't ever forget that. But let's just talk about magnitude for a second. V would be ds dt, which would be d theta r dt. R is a constant. D theta dt. This d theta dt, it looks like a W. It's the lowercase, it looks like a W. It's the lowercase Greek letter omega. D theta dt, this is angular velocity. This is radians per second, or revolutions per second, or degrees per second. So that right there would be R times omega, or omega times R. This is the angular velocity, and usually we said the lingua franca, the language that they like to use frequently, is with radians. The great, the great expressions utilize, Taylor's theorem utilizes radians when they talk about the great trigonometric function, those theorems, discussing those things, those theorems, those derivations. Taylor's theorem and then the derivations associated with it. They use the radian. The radian is the most natural to use. V is equal to omega times R. So that's interesting. What the heck? We kind of sort of entered this thing. I mean, we might as well talk about it a bit. R times omega, or omega times R. There's a lot here. Like I said, we'll come back and do some more. Let me see what else I can say. Just trying to argue with myself here a little bit how to proceed here. I do have another question to ask you. Wouldn't acceleration or magnitude of acceleration be dv dt? Magnitude of acceleration? Didn't we say this thing right here, V is omega times R? The R comes out, it's a constant. If you're taking the derivative of a function times a constant, the derivative of the quantity, a function times a constant, is just the constant times the derivative of the function. The R comes out, and you got this. R equals d omega dt. Well, this d omega dt, the change in angular velocity in radians per second, the answer is going to be, this is radians per second divided by seconds. It's radians per second. They call that alpha. Alpha looks like A, but instead of A, they use the Greek letter alpha for angular acceleration. So this is alpha times R. Alpha times R is A, and omega times R is V. Guys, there's something odd happening here. D is theta times R, or S is theta times R, or D is theta times R. It doesn't matter. You can use either one. It was just easier to do the derivative here. I didn't want to go d dt. It looks a little odd. If it was a capital D, maybe it'd be easier. You know, D capital D dt. Yeah, that maybe would have worked. But so I chose to use this one. But the S and the D are fine. You can use either one. Wow, this is kind of weird. And you're going to see this more in the future. Remember this, because you'll see it again. I'll talk about it again. But it's not going to be as shocking to us. What's going on here? Distance along the arc is theta times R. Theta is radians. Stay with radians. Whenever possible, stay with radians. It's your best bet. When they tell you, degrees is what's frequently used. And if they're asking you to calculate with degree, then do what they tell you. Obviously do what they tell you. But know that radians are very good, very, very good, as I've said many times. What's going on here, guys? D is theta, D is equal to theta times R. So let's see here. D is theta times R. V is this, which is that right there. And, alpha is, or rather A is alpha times R. You got this, and you got that. What the heck's going on? Be aware of this. You'll see it again. You'll see much more too. But there's analogies that go on between the translational realm, straight line motion, so to speak, and the rotational realm, going around in circles in a sense. If you want the straight line distance, take theta and multiply it by R. If theta's in radians, okay? All in radians. Radians per second, radians per second per second. Radians is good. If they're not in radians, you can convert it to radians. So I'm not going to make a big deal out of that. You know how to do it. But if you want the straight line distance, the amount of distance traveled around the circle, the amount of distance traveled in circular motion, you will go theta times R. Distance traveled in regard to circular motion, you'll go theta times R to find the distance traveled. Distance traveled is theta times R. The velocity as it's going around in circular motion is the angular velocity omega times R. The acceleration regarding what would it be in terms of linear magnitude, so to speak, at a particular instance, the linear type acceleration is alpha times R. Wait a minute. D equals theta times R, V equals omega times R, A equals alpha times R. D equals theta times R, V equals omega times R, A equals alpha times R. It's as though D and theta, distance and angle are analogous. This is translational. This is the translational realm. This is the angular realm. D and theta are analogous to each other. Translational realm, angular realm for velocity. Distance, angle. Distance, displacement, angular displacement. Translational velocity, angular velocity. Translational acceleration, angular acceleration. D and theta analogous to each other. V and omega analogous to each other. A and alpha analogous to each other. These are translational realm. These are linear realm. You take any of these and multiply by r, you get the other one. And that's where this is coming from. Very interesting. There's stuff we can do when we look at this stuff down the road. We'll refer to some of the stuff we did. We won't have to spend quite as much time on it because we're doing it now. But then later on, that's going to play a big role. It's going to play a big, this stuff right here is playing a big role, because then I can use those formulas for translational motion that we did earlier in the earlier discussions. Remember how we said D was equal to VF squared minus VI squared over 2A. D equals VIT plus 1/2 AT squared. We were talking about the pebble being thrown downward or something being thrown up into the air. We use those translational equations. We derived a lot of stuff. We said a lot of stuff. VF equals VI plus AT. When I replace the V's by omegas and the A's by alphas and the D's by thetas, all the equations hold. You're going to find that fascinating. We'll cross that bridge down the road. We talk about other stuff down the road. So this is just kind of a taste of that, and we'll see it again. We will come back to this. We will see this, and we'll play some games with it. Some pretty fascinating stuff that goes on. Very tempting. I mean, very tempting to look at this. It's hard to know when you want to get, when it's time to get on the merry-go-round and when to get off it, I guess, when you're discussing some of this stuff. But pretty neat. Pretty neat stuff. I'm almost tempted to try to give the derivation now, and then we'll look at it a little bit another time. Sooner or later, it's got to be done. So we'll see what we can say here. Let me look at it. You've seen some of the stuff I've done so far. Let me leave that stuff over there. Let me leave that stuff over there a bit, and let me erase over here. I'm kind of limited in the space I got, guys. I want you guys to be able to see what I'm doing at some level, or at least when you're on a bigger computer, you can see it a lot easier. But here it is. You're looking at it. Let me say something. I think when we see it again, it ain't going to bother us as much. Well, okay. We've said a lot of stuff. I guess as we talk, let's continue to talk. Do you guys remember we just said V equals omega times R. We've talked about that. We did a song and dance to get there, and we did it, and we got it. We got it right. We got it right. Well, how does this play out then? If V equals omega times R, here's your V. That's V. We just said V equals omega times R. Square that, divided by R. When you square this, R goes into here once. And that equals omega squared R. I don't like the way I wrote that too great, but kind of put this lower. Okay, some equations to look at. You got them. You got them in front of you. I give you a lot of opportunity to look at this stuff on your own and also have it in front of you when you're doing the homework and you're doing the exam, so you should be okay. So it's looking pretty good. Okay, well, it's just some interesting conclusion here. I'd like to say a couple other things. Say a lot of other things is what I like to say. We'll do it I guess in the time frame that we can do it. I'm kind of I'm looking at this and trying to make the judgment when to make the move. The move's got to get made anyway, guys. So sometimes I'm going to go into more content than the stuff I'm really going to be looking at, or at least what I'm going to be looking at initially. We are going to be looking at chapter 4 real soon, and then looking at a bunch of chapters after that, obviously. If that's the case, let's at least look at stuff ahead of things a little bit here. So this is a little bit ahead of the ball game, but we're going to see it again. And I'll have this labeled for you in a way that you can look at it, at least for the title of the video. So we got this. We look at some of that. What else can we say? Well, I'd like to talk to you some more. I mean, I'd like to say in this rotational realm that we're talking about, can we look at a few things and see what the heck's going on? Maybe it's useful. This is a good distance. You know, it can be a lot of this stuff can be a good distance down the road, but you got to know it by the end of the course anyway. So the sooner you get exposure to it, the better, I think. So let me continue with the lecture in that regard. Well, you saw what I wrote. You saw what I wrote down here, and you saw the derivation and everything else. We got to talk a little bit. And we'll see, and we'll be doing this analogy quite a bit throughout much of the course. There'll be other things we're going to add to it. When we talk about work, when we talk about power, when we talk about torque, there's going to be other analogies that get added on to what I've just done here. So this is just a beginning, I guess you could say, but a very important beginning. We can't know how to do the other stuff unless we're doing this. It's pretty important stuff. We know that distance is magnitude average velocity times time. We know that's VF plus VI, or VI plus VF, doesn't matter. Add the two, add the high and the low, whichever one of the, I don't know guys, this might be the high one and this might be the low one right here. Maybe this thing's going real fast and I put the brakes on it. Or maybe it's going real slow in the beginning and then I speed it up. But if this is for constant acceleration, this approximates it pretty good. We talked about a bunch of stuff, guys. We talked about acceleration. Over t, or over delta t. Delta t is probably a more accurate way to say it, but I'll say this. If you multiply by t and divide by a, if you multiply by a on both sides and add a VI, so there it is. We got that. And we did, you saw the derivations. You saw me do a whole bunch of stuff. We concluded VIT plus 1/2 AT squared. We also concluded VF squared minus VI squared over 2A. Okay, we've been there, we've done that. So what's the point? Interesting stuff. Interesting stuff can happen. Tell you what I'm going to do. I'm just debating. I'm just trying to debate here. What's the best way to show you this stuff, guys? I think either way is fine. I'm just trying to think which way is maybe a little more clear path to take it. Tell you what I'm going to do. If you're believing, even if grudgingly, if you're believing this stuff right now, if you just kind of, all right, I'll believe it for now. I'm not entirely comfortable with it just yet. It's going to take more time. But are you believing? Are you believing what's up there, or at least hope, or at least grudgingly right now you are, and they say, okay, well, let's see how this goes later on. Well, I'll tell you what I'm going to do. I talked about D equals theta r, V equals omega r, A equals alpha r. Is it true that D equals VI t plus 1/2 AT squared? You saw me derive that. You don't need me to derive that again. If you do, you're going to go back to my other video and you're going to look at it. You're going to see I had that derivation early on. The first video, chapters 1 and 2 for the Katz book, I went into that a bit. Okay. So if you want to see it again, go look there and you'll see it. I want to talk to you. We got to figure this out. Is D the same as theta times r? Yeah, I discussed that as well already. VI, I'll call it omega I times r times t. A, I'm going to call it alpha r times t squared. D equals theta r, V equals omega r, A equals alpha r. Got more questions to ask. I'm going to pull an r out of there. I'm going to pull an r out of here. I'm going to pull an r out of all these. Look at the math, guys. Look at the math. Sorry, I'm walking all over the place, guys. I want to make sure I get on film. I'm looking different places here. I want to make sure at least I'm having some contact with you guys when I'm doing this. All right. There's an r on both sides, huh? Why don't you divide by r on each side? Theta equals omega I times t plus 1/2 alpha t squared. That's pretty crazy. True. True story. Let's keep going. Look at this one. Didn't we say D was theta times R? In the analogy, in the stuff that we concluded. You may not have been incredibly comfortable with it, but I think you are at some level. You saw the derivation that I did earlier in this exact same discussion, this exact same video. You can do it. We know how to do it. We got to here. VF is the same. I'll tell you what. I'll put analogous to VF. I'll say omega F times R. VI, I'll say omega I times R. By 2A, A is alpha times R. You see how this thing plays out. What do you say? What do you say you divide by R on both sides? If I divide by r, if I put an r underneath on each side, if I multiply by 1 over r on each side, that r is an r squared. Omega f squared, r squared, minus omega I squared, r squared, over 2 alpha r squared. This is kind of crazy. We factor out the r squared, guys. R squared and r squared cancel. And you got this. Remember, you started way down here, ladies and gentlemen. Theta equals omega f squared, omega I squared, how about that? Neat stuff. You can play this a bunch of ways, guys. This is not the only way to do the derivation. I will promise you, you will get the same derivation no matter how you do this, as long as you're mathematically consistent. As long as you're mathematically consistent. As long as you're mathematically consistent, you're fine. Fantastic. I guess you could say theta would be the average omega times t. It's a lot like that. The average angular displacement would be the average between the high and the low, whoever that is, depending what kind of acceleration is taking place, as long as it's uniform acceleration, times t. That and that look a lot like this and this. The acceleration will be the final angular velocity minus the initial angular velocity times the time. You know that looks like this. You know that looks like this. You know that looks like this. Multiply by t on each side and divide by alpha. Looking like that. Multiply by alpha on each side and add omega I. All of these look like the corresponding parts here of all of these. All of that looks like all of that. Replace d by theta. Replace v by omega. Replace a by alpha. Make the d, wherever you see the d's, put a theta. Wherever you see the v's, put an omega. Wherever you see the a's, put an alpha, and bam, look at it. It's the same thing. Very important. We will use that through very much of the class. So I figured sooner or later we had to get some exposure to it. I gave it now. There's other ways you could have derived this. You could have started right here. You could have started right here with the thetas and with the omegas and with the alphas and how that plays out here. You could have started right here and then derived theta and theta being equal to this. Exact same answer. Different path to get there, but exact same answer. You could say, hey, look, man, I got this reality, that reality, this reality, this reality, and this reality. I got that, and then I got this, and this, all kind of related. They look just like those. Looks like that, and this, and this. Just like over here, the that, and the this, and this. They all look the same. From there, solve for theta. Use all the tricks we did when I was talking about chapters 1 and 2 with the linear realm, how you actually derive. You could have derived it just staying here without getting rid of the r's. The r's aren't even present if you start here in the derivation. And say, well, how would I do that? Well, I mean, I don't want to beat this thing up too badly, guys. But, I mean, you could look at it and say, how could I do it? Well, I could say, well, theta, just want to make sure this stuff is visible for you guys. Do a whole bunch of stuff here, guys. So, okay, I talked about the analogy here. Let me get that out of there. Just running out of room, guys. I just don't have the room I'd like to have, but man, it could be a lot worse. I've been in spaces where it's been a lot less room, so I guess we're very fortunate to have this, and we got great people helping me out. I mean, they've just done great work. So you're looking right here, you guys. You could say, okay, well, Mail it, where's he going here? How else could he derive that? I could have done this. I could have said theta's this. That's omega f plus omega I over 2 times t. I could have used omega f omega I over 2. I could use the other one. Forgive me, guys. I just want to make sure I got enough stuff. So I got omega f plus omega I over 2. For t, I can use change in angular velocity. The change in angular velocity divided by time is angular acceleration. Sounds good to me. So the change in angular velocity, there's no r here now, it's all angles. When you multiply by r, you get meters. When you don't multiply by r, you have radians. So these are just radians per second. Radians per second minus radians per second. The change in angular velocity divided by time is angular acceleration. If I do some mathematics, t is equal to omega f minus omega I over alpha. T equals omega f minus omega I divided by alpha. If you do this right here, guys, theta equals ladies and gentlemen, that looks very familiar. Theta equals omega f squared minus omega I squared divided by the product 2 alpha. Theta equals omega f squared minus omega I squared divided by 2 alpha. Yeah, I said that earlier. I derived it by getting rid of stuff, by getting rid of the r's. Here I'm staying with it. Okay, so when you had it here, again, I wish I had a little more room, guys, just not there, so we're going to make do. Bear with me. Make sure you get a good look at this stuff, though. So if I'm saying this, you're going to add the average velocity is omega f plus omega I divided by 2. I'm adding the high and the low, or the low and the high, whatever it is. It's got to be uniform acceleration, constant acceleration. If it's constant acceleration, omega f plus omega I added together divided by 2 is the average velocity. The time t, is given by omega f minus omega I divided by alpha. When we do it, we get omega f squared minus omega I squared divided by 2 alpha. Wow, that looks like D, that looks like V, that looks like D, that looks like VF, that looks like VI, that looks like A. Theta equals omega f squared minus omega I squared over 2 alpha. You could have done it just like that. Absolutely. And that's where you're getting that answer. The other way you could have done it is this, saying, okay, hold on, Bayless. You're saying, we're saying omega f plus omega I over 2 times t. Yeah, we've been saying that a lot in one way or another. Tell you what I'm going to do. Is omega f, if I manipulate this base equation right here, multiply by t on each side, and add an omega I on each side, I get this. Omega f equals omega I plus alpha t. Omega f equals omega, so omega f is omega I plus alpha t, right? And omega I is just omega I. See what we got here. Omega I and omega I is 2 omega I. Alpha t is alpha t. Forgive me. Right, correct, it is. No. So what I did was omega I and omega I is 2 omega I. We got alpha t right here. We got a 2 right here. We got a t right here. Okay. Let me see here, guys. I want to make sure you guys can see this, so I'm going to kind of, I got to erase something. I'll try not to erase anything just yet. Does 2 go here and go there? Yeah, it does. It does. 2 goes here. 2 omega I divided by 2 is omega I. Take the t. You guys know where this, I mean, you guys saw where this was going about 5 minutes ago. Let me just erase this. Let's multiply by t all the way across. Let's multiply by t all the way across. Multiply by t right here, multiply by t right here. Well, I don't think I'm surprising anybody over the last few minutes here on this, but theta equals omega I t plus 1/2 alpha t squared. Theta equals omega I t. Theta equals omega I t plus 1/2 alpha t squared. Very interesting. Here it is. It's the same thing as this. Theta equals omega I t. Theta equals omega sub I t plus 1/2 alpha t squared. And I solved that without even dealing with the originals. The originals were these. I could have gone right here and kind of just drew the analogy. Doesn't matter if it's rotating or if it's going in a straight line. Acceleration is acceleration in a sense. Displacement is displacement in a sense. And velocity is velocity in a sense. There's a difference. Angular velocity is the amount of angle that's been eaten up, the amount of angle that we've gone through, whereas translational velocity is the amount of actual distance that we've gone through. But if you multiply radians by radius, you actually get that distance. Radians are the angle, and the radius times the radians will give you the actual distance. They're completely analogous, though. If something's accelerating, if something's accelerating uniformly, constant acceleration, If it's angular acceleration and angles are being gone through, subtended as they say, if angles are being gone through, if there's angular acceleration, angular velocity, there's a constant acceleration, and you're actually covering amount of angular displacement, these formulas hold. Why wouldn't they hold? When you speed up, you cover more ground. In this case, you cover more angle. When you go slow, you don't cover a lot. When you go slow, you don't cover a lot of angle. When you go fast, you do cover a lot of angle. The analogy's alive and well, guys. This stuff works. I just showed you 2 proofs of it. And so it's not going to bother us when we see it in the future. We're going to see it, we're going to know, we're going to see it, we're going to know that there's an analogy there, and we're going to make our way through it. And when we need to make conversions from degrees to radians or from revolutions to radians, or at the end they don't want the answer in radians, they want it in revolutions, then we got to go from at the end we'll give our answer in revolutions, or we'll give it in degrees if they ask us to do it. We know how to do that. Okay? So this is the hard stuff, guys. The easy stuff they talk about is not that bad. So, see what else we can say here. All right. What else is there to say? Well, I mean, there's a lot. There's something we'll see more in the future, I guess you could say. You can. Let's go kind of to. This is a lot easier than what I just did. What I'm about to show you. But still, let's look at the big picture on this thing, and maybe it gives you something to kind of think about a little bit. In terms of radians. How fast, I'll do a little bit of what the book's doing, maybe a little bit beyond it as well, like I said. If you're talking about radians, we already said there are 2 pi radians in a circle. A circle has a total of 2 pi radians to go all the way around once. To go all the way around once is 2 pi radians. If you do 2 pi radians and you do it every capital T seconds, they call capital T the period, the periodicity. The period is how long does it take to go all the way around? How long does it take to go all the way around? Well, you're going to cover 2 pi radians in a total of T, capital T seconds. 2 pi radians divided by capital T seconds is omega. Is omega. Didn't we say that V was equal to omega times R? So V would be 2 pi over T times R. Wow. Yeah, that's true. That's all true. It's all true. Yeah, I guess it is consistent. Look at it. That right there got me here. That right there got me here. Yeah, I got another idea. What does 2 pi r mean anyway? Isn't 2 pi r the circumference? Look at it, guys. Isn't magnitude of velocity distance traveled divided by time? Divided by the time it takes to travel. Isn't the distance traveled to go all the way around, isn't 2 pi r the circumference of a circle? And isn't the period to go around once, didn't I just say it was t? I went from here to here, but I could have gone from here to here. You better be able to work it that way. We better be able to work it that way. The mathematics and the physics has to work, has to be consistent, or else you're in danger every time you fly an airplane, every time you go over a bridge, every time you go into a building. The mathematics, anything, the equipment, the medical equipment that's built, that saves lives, that helps people. All of that has to work, and it works when the physics is true and when the mathematics is consistent and when the logic is consistent. If it is consistent, in all circumstances, you're going to get to the right place. I just showed you a bunch of paths to get to different places. They're all consistent, so they all work. So we talk about something like this, so keep that in mind. There's a lot they say. I mean, there's a lot they say in other places, and we can kind of talk about it. We'll figure it out. Trying to think here, some other stuff I want to say. If the period is 10 seconds, capital T, 10 seconds, what does that mean? Well, there's this big circular track, and my race car going at a constant speed can get around the circular track. The circular track's pretty big. I mean, it's, I don't know, at the end of the day, it's a mile around it. It's more than a mile around it. It's 2,000 meters around it. And, whatever. There's some kind of jet they're testing or something like that, or whatever. Somehow it's on rails, and they can get around it in 10 seconds. Well, are you kidding me? How fast is that, Whatever. Try to make a realistic, I think of a good one. I mean, that's not the best. Let's say the track is smaller, and it's model cars or something. I'm trying to make this somewhat realistic, I guess. If it's 200 meters around, and it gets around, and you can get around one time in 10 seconds. The period is 10 seconds. What's the frequency? The frequency is the number of times you can get around in 1 second. Well, I can't get around that thing even one time in 1 second. It takes me 10 seconds to get around it one time. Yeah? 10 seconds to get around one time, huh? So what's the frequency? How many times per second do you get around? Well, let me take 10 and get the reciprocal of it, 1/10. I can go 1/10 of a revolution every second. The frequency is 1/10. Now, if somehow you could get around that thing in 0.5 seconds, what's the frequency? The reciprocal of 0.5 is 2. You can get around it 2 times every second. Why is that? Yeah, it only takes me 0.5 seconds. The frequency, F, is 1 over the period. The period is 1 over the frequency. Frequency is per second. They give it a special name named after the great physicist Heinrich Hertz. They call it a Hertz. The frequency is Hertz. It's per second. Frequency is 1 over the period. Frequency equals 1 over the period. Period equals 1 over the frequency. They'll go into that later. I figured it was, if they're talking about the period here, I might as well talk about something else as well. Okay. They get into some other stuff down the road. I mean, sooner or later, you got to kind of get into it. We talk some more. If there was a projectile fired, how would it, I've got to kind of pick and choose, guys. It's hard to summarize any one of these chapters that takes several hours, at least several hours, if you do it the right way. Depending on how long it takes to actually read some of this stuff, it's impossible to summarize that in an hour or two. But you try to do so. I mean, every teacher's going to try to do so for you. But you got to be reading that book and then use what I'm doing to augment it and the notes I've given you and everything else. I think you're going to be fine. I think we're going to be really good. We're going to be doing well. Let me talk about two-dimensional motion, and maybe I could talk about Newton as well. It's kind of a horse apiece, which one you talk about first. Either way, you gotta know how to do it, the stuff, guys. Let me talk a little bit. We talk about two-dimensional motion. If you were to fire a cannonball, they call that a projectile. What's a projectile? A projectile is something that doesn't have power after you fired it. A bullet fired from the gun has power while it's in the barrel of the gun, and it's getting acceleration as it's firing out, and you're going hunting to try to get some food or something. While it's in the barrel of the gun, it is being accelerated. It's gaining power from the controlled explosion that took place. But once it leaves the barrel, it has no more power source given to it. We're going to assume that the resistance due to the air, we're going to assume that air resistance is negligible. So once a cannonball gets fired from the cannon, once it's out of the cannon, it's not a rocket. It's not powered like a rocket is powered. Neither is the bullet flying out of the barrel of a gun. Once it leaves the barrel of the gun, the bullet does not have a rocket pack on it. It just goes because it's been fired. All right, well, let's talk. Again, this is very important. This is projectile motion. This isn't really a rocket. We will talk about rockets in the future, and a rocket that it gets fired, and then it still has a power source, its rockets, its fuel, that are getting it to go to where it's got to go. It keeps losing fuel, keeps losing mass, which makes it easier to accelerate it, actually. So it's kind of a weird situation. So a rocket's a different story. It's got something packed onto it. It's got something tied onto it, and it keeps getting power from somewhere. A bullet or a cannonball or an arrow, once it's fired, once it leaves, it doesn't have a power source anymore. It's projectile motion. Assuming no air resistance, there is complete symmetry in the path. All projectiles, in the absence of any kind of air resistance, any kind of drag, in the absence of any kind of drag or air resistance, follow uniform parabolic motion. They are mere reflections of one another on each side of the parabola. This is easier done than said. Let's just do it. Here's a cannonball, and it's fired from the gun, fired from the cannon. V. This is, VO. I think I'm trying to use different. I use differently. I use VI rather than VO. They use VO. I use VI. VO or VI, not a big deal. V naught means initial. VI is this. This is component VIX. Let me just see, you guys. I want to make sure I'm speaking. I'm going to try to speak the same language when I do this stuff. Yeah, there's a whole bunch of ways you can actually write it. Well, we'll figure it out. We'll cross every bridge as we need to cross it, I guess. VIY, VIX, fired at an angle of theta. This is not going to be a good drawing, but it's not going to be, hopefully not too bad either. And it lands. Where did it land? when at distance x, I sometimes write down r for range, capital R for range, but so we got this right here, you guys. And I told you there's perfect symmetry. Right down the middle. Up here, the cannonball's got no vertical velocity component. Notice velocities change. Yes and no. We gotta talk about that. There is no vertical velocity component at the very top. Why is that? Because at the very top, at that instant, that cannonball is not falling down. It's not, at that very instant, at the very top of its trajectory, that cannonball is not falling down, nor is it going upward. It is completely horizontal at that point. Got another thing to tell you. I'll put it this way. I won't go all the way there. This guy right here is VIX. That's VIY. That is also VIX. Right here it's VIX, and that might surprise you. What am I doing? I just called all three of them the same thing. Beginning horizontal component of velocity, middle horizontal component of velocity, very end horizontal component of velocity are all equal. In the absence of air resistance, if somebody were standing on a very high place and they say, we're going to do a physics experiment, person's going to have the rifle horizontal to the ground and they fire the rifle, there's no air resistance. And at the same time that person fires the rifle, somebody sitting next to him drops a spent bullet, drops a bullet that's already been out of the cartridge. It's the same mass, it doesn't matter if it's the same mass or a cannonball or anything. Somebody takes a bullet that they found somewhere, and it's already been ignited, already been fired, and at the moment the gun gets fired, the bullet will land 2 miles later after 5 seconds. When the other guy drops the bullet straight down, it also lands after 5 seconds. The horizontal and vertical components of velocity operate independently of one another. If I were to have some kind of dart gun here, and somebody just dropped the dart straight down, and the other person fired the dart gun, the darts both land at the same time. One lands 10 meters away from the other, but they both land at the same time. If I were to take a cannonball and drop it straight down, and I would take another cannonball and fire it from a cannon straight out, they will both hit, even if this cannonball right here lands 10 miles away, even if this cannonball that's been fired out of the gun lands 10 miles away, both balls will land, both cannonballs will land at the same time. That's crazy. The vertical component of velocity, the vertical and horizontal components of velocity operate independently of one another. In plain English, you fire it now. If you fire the gun upward, that's another story. If you fire the cannonball up like this, yeah, they're not going to land at the same time. They're not going to land at the same time. I can make them land at the same time if I do something to the other one. That's another story. For our purposes right now, just to kind of make the discussion proceed, if you fire the cannonball horizontally outward, completely horizontally outward, you fire it completely horizontally outward, it is going to land, the two cannonballs are going to land at the exact same time. In other words, if you kind of break up the two components of velocity, It's as though they behave independently of one another. What does that mean? That means the cannonball here, when it's going up, still is VIX right here. When it's coming down, still VIX. Wow. The vertical component, however, is not constant because it's under the influence of gravity, the same way that anything would be under the influence of gravity as far as having its acceleration change. I mean, they're all under the object is generally under the influence of gravity, obviously. You fired it upward, what happens to this thing? When you fire this thing upward, this component right here gets smaller and smaller. It goes to 0. So what is going on? So what is going on? Well, how does anything lose velocity? Well, you saw what happened earlier, guys. We threw a rocket up into the air. We launched a rocket up into the air, and it just became a projectile. This time it became a projectile. We didn't have any fuel on it. It was not really a sophisticated rocket. It was not really a sophisticated rocket. So it was just a projectile. We fired it up in the air. How long did it take to get to the top? How fast was it going initially? How high did it go? Et cetera, et cetera, et cetera. How high did it go? How long did it take? How fast was it going initially? These are questions we can answer. How can we answer them? How about you answer them this way? Do you guys remember in one-dimensional motion? VF equals VI plus AT. Got a question to ask you. This is completely symmetric. What does that mean? It means it takes time, small t, to get up to the top, and it takes time, from down there, it takes time, small t, to get to the top, and it takes time, small t, to get to the bottom. The total flight time is 2 times small. The total flight time, I'll call it capital T. They don't do that sometimes. Who cares? We try to differentiate everything here. The total flight time, capital T, is equal to 2 times small t. It takes time. If it takes 10 seconds to climb, it takes 10 seconds to fall. There's perfect symmetry. If this whole thing is 500 meters, the middle of it is at 250 meters. Fascinating. What is going on? Well, there's a lot going on. Can we say this? VFY equals VIY plus AT. The acceleration is negative g. So what's going to be here, VFY equals VIY plus negative g. We'll say g is positive. We'll give it a positive amplitude. Negative g is negative 9.8 because this thing slows it down. At the very, very top of the journey, you understand that VFY equals 0. There is no arrow going up for VFY, nor is there an arrow going down for VFY. At the very top, it's 0. Let's add a positive GT on each side. Let's divide by G on each side. We're not done. We're not done, but this is pretty important. Now what? Can I ask you a question? Is VIY equal to VI? Look at it. Look at the trigonometry, guys. We've done a lot of songs and dance on this one already in the short time we've been together. We've done a lot here. It gets fired out. VIY is VI sine theta. Or V naught sine theta. It means the same thing. VIY is V naught, V0. VIY is V naught times the sine of theta. The time it takes to get to the top, ladies and gentlemen, is VI sine theta divided by G. That's the time it takes to get to the top. The total flight time is double what this is. Sometimes they call the VI, they just call it V. Just double it. What's the maximum height you could attain? It's kind of neat. There's a lot we could say here. May I ask you another question? I mean, I guess I'm just debating with myself where to go with this, but okay, so that's kind of some of what's going here. Make sure you're rewinding this thing when we need to do so. Take a look at it, okay? If you get to there, let me ask you some more questions. Is the total distance x going to be equal to v sub xi? Or is that VIX? VIX, doesn't matter. The VIX they just call VX sometimes. No big deal. It's VIX times T. Am I justified in saying something that simple? Yeah, I am. But there's more complications that come into it. And why am I justified in saying that? Why am I justified in saying that, ladies and gentlemen? I'm justified in saying that because VIX is this. VIX is this. VIX is this, okay? VIX is this, VIX is this. I guess I beat that into the ground. VIX is the same thing throughout. It's a constant speed. Constant speed times time will give you the distance. Sure true. That is sure true. Is it true that VIX is it true that VIX is VI cosine theta? Yeah, it's all those trigonometric tricks that we've been playing, guys. Vectors behave like triangles do, right? I mean, you don't add it like money. You don't resolve things like money or like mass. You resolve vectors in terms of triangles. Pythagorean theorem. Some beautiful trigonometry that's out there. Using the exponential function to actually derive a lot of that trigonometry. I've already talked about that. It's absolutely okay. Just see if that printed out okay, guys. Forgive me a second here. Yeah, it should be okay. Wait a minute, what are we talking about? Yeah, that's what I'm talking about. Wait a minute, did we just say T was that? Okay. Getting closer. Yeah, I'm not going to give that as a final answer, but that's true. You guys just saw me do it. You guys just saw me do that. Yeah, well, there's something here of interest. If you use, and we're not going to do this. I just want to tell you, if you use this beautiful equation, if we use this beautiful equation, e to the I theta is cosine theta plus I sine theta. If you use that beautiful equation, guys, you can conclude that the sine of 2 theta equals 2 sine theta cosine theta. And that simplifies that a little bit. Put sine 2 theta there. So at the end of the day, put this whole thing becomes sine 2 theta, and it makes it a lot easier to deal with. And they use V naught squared. They use V. They use for VI. They use V. You know, VI can be V naught, can be V. You know, we're not going to split hairs on that. Just know that it's kind of the ultimate one, the one that started right then and there. The big thing is know what you're doing. The sine of 90 degrees is the biggest sine that you can get. The sine of 90 degrees is 1. The sine function cannot get bigger than 1. The sine of 90 degrees would be 1. You get the biggest answer there. How do you get that? You fire it at a 45-degree angle. If you're a shot putter, let that shot put fly at a 45-degree angle from the ground. If you're a baseball player, you're throwing that ball, football player, 45-degree angle, assuming there's no wind to mess you up. If there's wind, you got to take other considerations into account. Why is that? What's 2 times 45 degrees? If this is 45 degrees, 2 times 45 degrees is 90. Sine of 90 is 1. That's the biggest you're going to get. Makes sense. You hit it right at that angle. If you can shot put it at that angle, you're doing pretty good. So you got this guy right here. Neat stuff. Somebody might ask you, what's the highest this thing can go? The highest this thing can go is right here. That's the highest. That's the highest. There's a lot of ways you could do that one. How about this? The height is h. You understand there's a great amount of velocity early on, and there's 0 velocity at the end. What do you say I average the two? Because the acceleration is a constant acceleration. It's called a deceleration. It's called negative g. It's called negative 9.8 meters per second per second. and then multiply by the time. Tell you what, I started out how fast? VI sine theta is how I started, right? That's the initial velocity, VI sine theta. My final velocity is 0. I'm going to add them together, divide by 2. Add them together, divide by 2. Then I'm going to multiply by the time it takes to get halfway up there. That's VI sine theta over G. Is that believable? It is to me. VIY is a lot. It's a big arrow. There's no arrow up here. Let's average the two arrows. It's a constant acceleration. VIY is VI sine theta. VIF is 0. VIY is VI sine theta. VIY is VI sine theta. VFY is 0. Divide by 2. 0 in this, divide by 2 times this. VI squared, sine squared, 2G. VI squared, sine squared over 2G. Could you have done it another way? Yeah, sure. How about VF squared minus VI squared over 2G is going to be the height. How about this guy's 0, the final VIF, VFY, VIF, I can't remember which subscript I put first. It doesn't matter, guys, as long as you know what you're doing here. VFY squared minus VIY squared over 2G. VFY squared minus VIY squared over 2G will get me there. VFY was 0. VIY squared is this. The acceleration is negative. It's a negative, so that's negative 2G. Negative VI squared sine squared theta over negative 2G. What's negative divided by negative? So that's the height. And that's how we're playing the game. That's how you do a lot of this stuff, you guys. That's how you do a lot of this. This is going to help us in problems we do for problem number 4. There's a lot here, obviously, guys. You've got it in the notes. You've got it in my written notes more than anything. If you're not comfortable with the videos, audio videos on it, you also got it on the written notes as well. Okay. Let me say something else, since I guess we're kind of on a roll here. Let me talk about Newton's laws of motion. You got 3 laws of motion. Let me talk about them relatively quickly. We'll obviously talk more about them as we proceed with various problems that we encounter, and we'll figure it out from there. So let's see what we have here, guys. All right, guys, since we got this far, might as well sooner or later we got to encounter this stuff. So let me talk to you about it as I can. Newton's laws of motion. Regarding this, let us talk. First law of motion, often called inertia, the law of inertia. Second, F equals ma. Third, action, reaction. What do we got? Well, give me here something. I'll kind of just read it verbatim from there, and I'll kind of give my own kind of take on the whole thing a little bit. Reading right from the book. This is chapter 5, but of Newton's laws of motion here. Number 1, close translation of Newton's first law. Every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. More contemporary statement of Newton's first law. If no force acts on an object, then the object cannot accelerate. So that's the first law of inertia. We'll talk, I kind of said it a little differently. I kind of summarized it a little, I use the word inertia, but the first law of motion, guys, is basically this. Every body continues in its state of rest or of uniform motion, whichever it is, guys, in a straight line. It's either at rest or moving in a straight line at constant speed unless it is compelled to change that state by forces impressed upon it. If no force acts on an object, then the object cannot accelerate. That's a big deal. Newton's second law. The net force on an object is 0 if and only if the acceleration of the object is also 0. I'll talk more on that. I'm a little different in my approach on that. But number 3, Newton's third law. If two objects A and B interact, the force exerted by A on B is equal in magnitude to the force exerted by B on A, but in an opposite direction mathematically, one on the other. Okay. Let's talk. Maybe this is a little easier if I talk about it as well, just my own words. Number 1, Newton's first law of motion. A mass that is not moving or is moving at a constant velocity will continue to do so unless it is acted upon by an outside force disrupting that equilibrium, so to speak, disrupting that circumstance. If the object is at rest, it will remain at rest unless an outside unbalanced force acts upon it. What's a force? A force is basically a push or a pull that will tend to cause a change in a state in motion. A push or a pull that will tend to cause a change in the state of motion of something. I exerted a force on this. How did I do that? Well, I tried to push the refrigerator so I could move it. I tried to push the car so I could move it. I tried to pull the car so I could move it. Either myself with my own strength or with an automobile, whatever, with some other vehicle or something. An object at rest will remain at rest unless acted upon by an unbalanced outside force. An object in motion in a straight line will remain at constant velocity, in a straight line unless acted upon by an unbalanced force. Mass has a sluggish tendency to it. That's why in the British system of units, the unit of mass is the slug. The unit of weight is the pound. For us, the unit of mass is the kilogram in the metric system, and the unit of weight is the Newton. Okay, we use pounds, but newtons and pounds are analogous. They're units of weight. They're units of force. They call it the slug in the British system of units. Why is that? Because mass has a sluggish tendency. If it's at rest, it'll stay that way unless you act upon it with an outside unbalanced force. If it's in motion in a straight line at constant speed, it will stay that way unless you veer it off course, speed it up, slow it down, or move it off course by an outside unbalanced force. The more massive something is, the harder it is for you to change its state of motion. That makes sense. That's the first law. Second law. Essentially, there is no, I'll try to, the acceleration of an object is proportional to the total force. These are so closely related, man. It's hard to, there are three laws, but they're all kind of interplayed. They all actually validate one another. If an object is very massive, and you give it a very great change in its state of velocity that it initially had, you give it a final state of velocity that's much different. If you change its velocity quite a bit, give it a great acceleration in a short period of time. If you change its velocity in a short period of time, and it's very massive, a great acceleration on a great mass, a great acceleration on something very massive requires a tremendous amount of force. I can make this eyeglass case accelerate quite greatly, I guess. I can get it to 10 meters per second. I can give a great acceleration to it. Sure. Try doing the same thing with your own physical power, no external machine. With my own power, I can give this thing a great acceleration. Try doing that to a truck that's parked, even if it's in neutral. You're going to need a tremendous amount of force, much, much, much more force to do that with the truck than you needed with this case. How much more force, by the way? How many times more massive is the truck compared to this eyeglass case? How many times more massive is it? Let's say it's 1,000,000 times more massive. Then you need 1,000,000 times more force to generate the same acceleration. Action-reaction is pretty fascinating stuff. Rockets work that way. Just about everything works that way. You got to be careful. Action-reaction means if I throw, that's why major league pitchers have such a problem with their shoulders sometimes. Nobody's hitting them. They're not playing football. They're not playing rugby or football. Nobody's hitting them. Yeah, but they're throwing something. And the force that they put on that ball, in a sense, puts on their arm as well. If I this sounds kind of stupid. If I run into a wall, I think I've done that in my life anyway, but if I were to run into a wall, I'm going to do something to the wall. I'm going to exert a force on the wall. The wall's going to exert a force on me as well. So, there's a lot. So it's actually, the force that I put, and people sometimes, it's kind of a misnomer how that all works out. Gravity's a great example of that. I can be in outer space, let's say, I'm wearing a spacesuit, whatever. The Earth is pulling on me. The Earth is pulling on me and does what? Well, it's pulling me toward its center. We'll talk more about that when we have to talk about it. But the Earth is pulling me as though it's pulling from its center of mass. Center of mass is the center of the Earth, let's say. It's pulling me towards its center. It's pulling me toward its center of mass. So I'm getting pulled toward the Earth, toward the center of mass. What's happening to me if I get pulled towards the Earth? I'm being accelerated. It depends where I am. If I'm very far away, it's not 9.8 meters per second. This thing just shut down. It's on again. Okay. If I'm going at 9.8 meters per second, close to the center, close to the surface of the Earth, I may have an acceleration of only 5 meters per second if I'm far away. But anyway, it's pulling me. Let's say I'm close. Let's say I got a bungee cord on me or whatever. I got a parachute, and before I pull the parachute, I am being yanked toward the center of the Earth. I'm being yanked toward the Earth. Yeah, I am. There's a force of gravity on me, and the Earth is pulling me, and it's making me accelerate pretty fast. Almost, I don't know how fast. 9, 10 meters per second, right? 9, 10 meters per second, 9.8 meters per second. You know what, though? The Earth is pulling on me. I'm also pulling on the Earth. My mass is also pulling on the Earth, and I'm pulling the Earth toward me. The Earth is not coming at me the way I'm coming at the Earth, because the Earth is multitudes, myriads of times more massive than I am. The Earth is being pulled toward me by me, but its acceleration might be 0.0000001 meters per second. The Earth's getting pulled toward me just a little bit. I am exerting the same amount of force on the Earth as the Earth is exerting on me. Then how come the Earth's not moving? Because the Earth's a lot more massive than I am. So that's kind of action-reaction. The Earth is pulling me, let's say this is the Earth. And this is me. This is the accelerator. This is my mass, small mass. That's the Earth. And I'm getting accelerated A1, whatever. The Earth is getting accelerated. This, I shouldn't even draw it. You can't draw it. But it is action-reaction. The Earth is experiencing the same magnitude force from me as I am experiencing from the Earth. Same magnitude force, opposite direction. Earth is coming toward me, I'm coming toward the Earth. I will get closer to where the Earth originally was than the Earth coming closer to me where I originally was. It's so much more massive, it's practically not moving. But it is moving. The Earth is suffering a force because of me. And I'm suffering a force because of the Earth, and it's the exact same magnitude force. It's opposite direction. And that's what they're talking about, these. 1, 2, 3, Newton's 3 laws. And we'll use that when we're doing some of the stuff on there, guys. We'll see. I think when we do the problems, this stuff comes out pretty good. What I'm going to do is I'm going to let it go right now. I know I said at the beginning I was going to start doing chapter 4, and I basically did a lecture on 2 or 3 chapters, which is something we had to do anyway. So we are going to do chapter 4, the next video, and then proceed from there. Because we got a lot of the lecturing out of the way for us as well for a good amount of the stuff coming up. So we should go pretty smooth on that. All right. Thank you for your time, guys. Let me shut this off.